Okay. I think this was number 2. And we just talked about it, but let's just write it out. Okay, so we know that this is 37 degrees. Because I told you the angle with vertical is 53 degrees, that means your angle with horizontal is 37 degrees, and that's the angle you want to work with. And I did the angle with vertical just to make you aware that you need to read carefully. If you use 53 degrees, you can still get a result. You have to work on a 53-degree plane. I think you'd have pretty high coefficient of friction. So be it. What we're trying to find then is if this thing goes from here down to here, gains, it attains a velocity of 3 meters per second, want to know what the coefficient of friction is. Well, if you start thinking about the coefficient of friction rather than what's going on, you might never get there. Okay, what's going on is energy. Okay, this thing descends a certain distance, so its gravity does that certain amount of work on it. Okay. Now we could say that the work done by gravity, it's a little more complicated, but not badly. Okay, is negative mgj, which is your gravitational force, dotted with your displacement vector, which is 6 meters. It's 4.8 meters I minus 3.6 meters times j. And the dot product is then just going to be, well, it's going to be negative 3 meters times mg, and I've got m for meters and m for mass, which is not a good idea, but plug in the numbers and stuff, okay? So just do the dot product. And that goes back to the first problem. You know, how do you answer the first problem? You guys dispense with that pretty quickly, I hope, because you understood that you just do the dot product. Now, if you don't remember what the dot product is, and, you know, majority of the class right now is in multivariable calculus, so, you know, we've had a good review of that. But if you don't remember, go back to the first chapter of your text. It's very simple. And make sure you understand how to do a dot product. Okay. Change in kinetic energy. Well, use a given velocity and mass, you get the change in kinetic energy. Okay, what's the work of friction? Well, work done by gravity plus work done by friction is a change in kinetic energy, because this is the work by the net force. And the net force is the sum of the frictional force and the gravitational force. Those are the only forces that do work. You do have a normal force, but it's perpendicular to the direction of motion, so it does no work. The force has to have a component in the direction of motion before it do work. And that, of course, that goes right back to dot product, but that's the concept behind the use of the dot product. Okay, so there we have that. Okay, and I hope that makes sense. Again, it just comes down to this plus this equals this. Because change in kinetic energy is the work done by the net force. Okay? And that's your work energy theorem. Okay? It's your starting point for almost all of these problems. How do you do the work energy theorem? How do you apply the work energy theorem? Okay. Well, then we have this situation. You have a 1.5 kilogram cart. You have 3 joules done by the net force. Well, that means the kinetic energy, if you started from rest, is going to be 3 joules. So you get V equals what? Well, again, you've got the kinetic energy, you're given the mass, solve for V. Nothing more to it. Now, if gravity does 2 joules of work, isn't mind if this thing's on a decline. Gravity do plus 2 joules as you're going down the incline. And again, how do you get that? Here's your displacement vector. Here's your gravitational force vector. Okay? This displacement vector has a vertical component. In other words, delta S is delta S x I plus delta S y j is your delta S. But if you do the dot product, it's only the j component that matches up here. If you're going down the incline, they're in the same direction, so that you're going to have a negative j component here multiplied by a negative j component here, giving you a positive result, so your work is positive. Intuitively, going down an incline increases your kinetic energy, so you know that the work done is positive, right? So in other words, then you conclude that, okay, that adds 2 joules to the kinetic energy you get from the system. Well, now if you're going up the incline, then your delta S y would be in this direction, be positive if this is negative, and you get a negative work, which would then leave you with 1 joule. In that case, this is 5 joules. And you then easily find the velocity. Now, if there's an additional 1 joule against friction, that implies the kinetic energy is 3 joules plus 2 joules minus 1 joule. Because if you're doing positive work against friction, friction's doing negative work on you. And now you can easily find V. Same way. Okay? So if you think in terms of energy, these situations get very easy. But you got to learn to think that way. You got to learn what to look for, and that's why you do a lot of problems. I would recommend reviewing some of the problems you've already done and be thinking about these ideas as you do the homework tonight and the homework for Monday. Now for Monday, you have the idea of potential energy. The 3 joules done by the net force here means that your system is giving up 3 joules of energy. Okay? So the system must have had 3 joules of energy to give up. Well, that's a potential energy if it depends on position. That's potential energy that depends on position. For example, you bring these magnets together, the closer you bring them, the more potential energy you have. Okay? It's the way potential energy behaves. So that's just one example. And think back in terms of that experiment with the carts and the magnets. Or with the carts and the rubber bands. Or imagine a cart and a spring. And another thing about a cart and a spring, let's see, in this situation, it might be that this negative 3 joules is due, or the 3 joules you get here is due to a spring expanding instead of a magnet repelling, right? So when you have something that starts with a velocity in the direction of that spring, it'll compress the spring, and the spring will do the opposite work. An ideal spring will do that. Okay? Rubber band doesn't do that, doesn't exert a force due to compression. An ideal rubber band bone, well, yeah, we'll talk about that. And you'll see that. You need to know how to get the work done by spring. It's a simple integral. If you can't do the integral, don't worry about it. Just use the formula 1/2 kx squared. Okay? And you've encountered that. I think you've encountered that in the problem so far. If not, you're going to encounter it. Simple formula that follows from the linearity of the spring, and K is the slope, the linearity of the force with length. Slope of that graph is your K. So you put all that together.